Okay, so when we look at the entirety of this unit and we start all the way from the beginning, really our first thing we were looking at was what is fire? And the question is, well, why on earth do I start with what is fire? Well, fire is kind of a weird thing to look at. I mean, we get to this whole idea of is it matter or is it energy? Is it something else entirely? And what I like about talking about what is fire is I get you guys to this idea of like, I don't know which one it is. Because that spawns perfectly into our next thing is okay, well, we have a generalized idea that fire is something. We just don't know what it is to call. And we can take this information and build right into thermal energy. Because thermal energy is pretty easy for you guys to comprehend. You've seen this before. And so we talked about the main three. We talked about conduction, which would be direct contact with one object to the next. We talked about convection. Sorry about that. Where we've got a generalized flow of warm materials rising up and cooler materials rising down. And this could happen as a solid inside the Earth's mantle. It could happen as a liquid just in a pot of water, or it could happen as a gas just sitting basically in the air or inside of an oven. And then we got into radiation, which when we say this, now that we know more about radiation, this means non-ionizing radiation. Basically traveling energy across from one spot to the next is what we're really looking at. But this got us to a point where we could start to say, okay, there's something happening with energy. And fire was a nice bridge for us to start off of because fire we all have some familiarity with so that we could understand, okay, how are we going to get energy to flow? But for the most part, this was not the hard stuff for you guys. So where this got a little bit more challenging for us is when we started talking about the Big Bang. Because we all know the Big Bang is a thing. We don't really understand exactly all the pieces of evidence. Well, maybe you do, but for generalized speakings in terms of chemistry, this one becomes a little bit more challenging. So I tried to hone in into three big pieces of evidence that were proof for the Big Bang to be more than just an idea. And that first one we looked at was this idea of what's known as red shifting. Now, red shifting means if you look out in the known galaxies, anywhere, if you look at any object, with the exception of the Andromeda Galaxy, which that's beyond this course, everything is shifted to the red side. Meaning if I have some normal set of spectral lines that I find in a lab, and I looked at the exact same elements further away, they would be shifted more like this. Or maybe we don't even see all the lines because what's happening is that the light itself, which is normally about this length, as it travels between Earth and wherever this object is, the light is being stretched toward the red. And so that's a direct indication with redshifting that the objects are spreading out from one another, and everything sort of is the center, all spreading out from all different directions. So redshifting is definitely an indication that we started from some singularity and it's spreading out. But beyond just redshifting, because that's one piece to look at, there is something called the cosmic microwave background radiation. And so what this is if you took a picture of the entire universe, and they usually show them like this, you see all these blotches out there and whatnot, and I'll put a better one in there so you can see it right there. What this really means is this is sort of the smoking gun of the bang. If you took all the light, started really high energy at the very beginning of the Big Bang, and you let it stretch out so it's almost like a straight line, what you'd basically find is that this kind of light is a microwave. And this particular light is about 13.7 billion light years away. This is the oldest known light in the universe. So the cosmic microwave background radiation is an indication that the oldest light is 13.7 billion light years away in all directions. It's sort of the smoking gun of the Big Bang. This is also the one we spent the least amount of time describing, so it's okay if we're not perfect on this, because the other one kind of got to where we were going. And the other one that we started to look at is this idea of element abundances. So if an element has a high abundance, you would imagine that it formed early on in the universe. And what we see is the vast majority of the universe is hydrogen, followed very closely by helium. But then the rest of our periodic table, if I'm drawing one out, there's almost nothing to it. There's very few amounts of everything else besides, okay, some of these other ones, like we got carbons inside there, we got some oxygen sitting in place, but there's tons of hydrogen. And then there's a lot of helium, which would make sense if this is the smallest piece. If the smallest form of the elements that exist, or the smallest form of matter that exists, is hydrogen, you would expect to have lots of this. And we do. And so not only is light shifting or spreading out, we have some background light that's sitting at 13.7 billion light years away, but we also see that the pieces in the universe, the smallest ones, are in the greatest abundance. And that's our generalized idea for proof of the Big Bang. And what this did is this took us further into the development of, okay, if we understand that matter does exist, what does matter actually look like? And so we went through this entire idea of the history of the atom, right? And we said, okay, the history of the atom, we've got this sphere, da da da. Eventually, we find out the sphere's got some things inside of it called electrons. Or like, actually, the nucleus is in the center and the electrons are rotating around, so not a big deal. Actually, the electrons aren't really rotating around exactly like that. It's more like rings. Actually, they're not doing that at all. There's protons in the center, and there's some probability of where you're going to find it. Actually, there's one more piece to it. There's also a neutron sitting inside there with these probabilities of where they're going to be. It's like, okay, where are we? Well, we end up settling with this idea based off all the historical evidence that there's protons in the center, there's neutrons in the center, and there's electrons that are somewhere on the outside. Now, are they rotating like the planets? No. What are they doing? Wait, we'll get there. Okay, they're not doing this orbit in any sort of direction. They're doing something kind of strange. But this was allowed to basically tell us, okay, well, we can figure out mass because that would just be our protons plus our neutrons. Electrons don't have mass in the ways that we're looking at it. They're 1/1000th or 1/2000th the size of a proton or neutrons. We're not so worried. We could look at charge, and charge would help us a lot because protons are positive and electrons are negative. So the charge of any atom or ion that it's charged ends up just being the difference between the protons and electrons. And this is great because this could help us to balance out nuclear equations. And with nuclear equations, what we could then do is look at the idea of the three major types: alpha, beta minus, and beta plus. And so if we had an alpha decay, we had something like, I don't know, polonium-210. And polonium-210 would radioactively decay into a 4-2 helium nucleus, which was an alpha particle, and then some unknown piece. Well, polonium is the 84th element, so it actually has 84 protons. So if we're going to conserve charge on both sides, this one better have 82 protons, and it better have a mass of 206, and so we find out this is lead. So polonium-210 readily radioactively decays into lead-206, and this high-energy alpha particle comes off. In beta minus, we have things that are going to end up making electrons, okay? And in beta plus, we have things that are making positrons. And it doesn't really matter what our starting values are. Our masses stay the same, but we start converting protons and neutrons. So in this case, this has to be up by 1. You essentially made a proton. So you're going to take a neutron and turn it into a proton. And in the process, you're going to shoot off this high energy electron. Here, the atomic number is going to go down by 1 to conserve the charge. So that means we just got rid of a proton. And the only way to get rid of a proton is to turn it into a neutron, which led us to this whole idea of the band of stability, where we have this line and we have the band of all the radioactively active isotopes up to number 82. And if we look at the protons versus the neutrons, we can actually use this to predict what kind of decay will take place. So after about 82, there's no kind of stable isotopes. So this whole section out here is going to be our alpha decays. And so if I give you something that's got an atomic number that's bigger than 82, like polonium, we know it's going to be an alpha decay. Where it gets tricky is if we're under 82. So let's take, for example, carbon-14. Carbon-14 in this case should have 6 protons and 8 neutrons. Well, that's a little bit neutron heavy here. And in that case, what that means is we're going to take a neutron and turn it into a proton, which is a beta minus. So carbon-14, 6, will end up making 14, 7, or nitrogen, because it has to drop its neutron and add a proton to reach the band and become a stable form. A little bit weirder than that is, what if we have something that's heavier amounts? So we have something that's, I don't know, sitting somewhere down here, and now it's proton heavy. That'd be our beta plus. So a lot of times they'll talk about something like carbon-10 as an example of that. So in carbon-10, we have 6 protons and only 4 neutrons. So we're sitting really, really low here. And if that's the case, and we have carbon 10, and we're going to do this, we're going to end up making something that has 5, mass of 10, boron 10, which is a lot more stable. And we'd have a positron emission in this case, so we would need to get rid of a proton and then change it into a neutron. In either case, what we're ending up trying to do right here is just convert to a stable type of nucleus. Either way, when we do this, we're just balancing mass and we're balancing charge kind of as we go through this, whether with a chart or with not. And the last thing really to make mention is this idea of nuclear fission versus nuclear fusion. So when we talk nuclear fission, these are all of our alpha, our beta minus, our beta positive, our gamma, everything on there. This is taking a nucleus and it's breaking it into smaller pieces, or it's breaking off high energy particles. Fusion is actually building. And we didn't talk too much about this except if you were to visualize a star. Because in the center of the star, it's being powered by hydrogens in various forms interacting with each other, start building heliums. And in that process, a ton of energy is coming off. Nuclear fusion is how stars are powered. Fission is still a possibility for how we're going to look at this idea of, atomic bombs, other sources of radiation. And we talked a little bit about the radium girls because it's a fission involving radium in that particular case. But if we're going full circle, fusion is where we started. In the Big Bang, we had a ton of nuclear fusion take place, in which case we made some unstable isotopes, which then radioactively decayed into a fission-like existence. That should be enough to sort of take you full picture as what we did that first unit.